Alright, welcome. In this video we're going to be recapping CalBC Unit 3, which in my class is all the analysis of f prime and f double prime, the relationship between a function and its derivatives. And I've got the notes book right here, so I'm just going to kind of quickly remind you of what all we talked about. And, in the first lesson we talked about the first derivative and what all it could tell us. And we talked about the definition of a critical point, intervals of increasing and decreasing, maximum and minimum using the first derivative test, and we talked a little bit about motion. Okay, in this video, I'm going to kind of go through first derivative, second derivative stuff, which was 3.2, and then I'm going to save all the motion until the end. Okay, I'm thinking that that'll be the way for us to go, to do all the motion stuff at the end. So I'm going to do this, then I'm going to fill in that grid on the backside, which is the relationship between f prime and f double prime, what we're looking for when we're thinking about all of these things. I'll fill that in on this video, and then at the end, I guess, but before I talk about motion, I'll do a couple of absolute extrema questions. All right, so let's get to it. We started with 3.1, and that was just like all about what a first derivative could tell us. So 3.1 is f prime of x, really. That was what we were studying. Okay, so with that, I think the first thing that we had was the definition of a critical point. And that's going to be important, and so I'm just going to start there. So remember that a critical point is a place where the derivative is 0 or undefined. Let's get that over a little bit. Okay. Critical point of a function f is where f prime of x is either equal to 0 or f prime of x doesn't exist. It's really easy to miss the ones where f prime doesn't exist, especially when f is given to you algebraically. If you got like your derivative having negative powers, and thinking about where it doesn't exist, you would need to rewrite those negative powers as fractions, I think, to most clearly see where those derivatives are non-existing. Okay, then from this, we kind of went and started talking about, okay, what if the slope is positive? We're going to say the function's increasing. So intervals of increase and decrease. So f is increasing anywhere where its derivative is positive, is what we said in this class. Okay, we mentioned that maybe out there's another definition of increasing that might be a little better, a little more robust, but for AP Calculus, we're going to say where the derivative is positive, where the slope is positive, the function is going to be increasing. Okay, and then we could say that f is decreasing anywhere where its slope is negative. Okay, and then we talked a little bit about maxima and minima, and then so a maximum is going to be a place where the function was increasing and now it's decreasing, and a minimum would be where it was decreasing and now it's increasing. And well, I've got a bug in here. So I think I'm just going to write those in, but I don't think you need to watch me write that, so I'm just going to copy it in real quick while it's paused. All right, there you go. So I think what I really wanted to point out is that, first of all, at a relative maximum, the derivative is either 0 or undefined, right? And so that's, all extrema come at critical points. Okay, that means that critical points are potential extrema, but not guaranteed extrema, right? Because, think about the graph of y equals x to the 3 at the origin. It's increasing and then it goes flat and then it increases again. It would have a 0 derivative there, but that's not going to be a local maximum. Okay, and then also the other thing I wanted to point out, that when using the first derivative test, which is what we're talking about here, the sign of f prime changing, your reason just always wants to be for a relative maximum, the derivative of whatever went maximum changed from positive to negative. And the reason for relative minimum wants to be the derivative changed from negative to positive, if we're using the first derivative test, which we learned in this unit, we're mostly going to be using the first derivative test, and then it's, in the next couple of units where we're going to be forced to use the second derivative test. Okay. One other thing that we talked about in the 3.1 lesson was the mean value theorem. Okay, and the gist with the mean value theorem is that if a function is differentiable over an interval, and that's going to be the big if f is differentiable, then there's got to be some place on that interval where the instantaneous rate of change is equal to the average rate of change. So I'll just write that in. All right, so once again, if f is differentiable on the interval a to b, then we'll have some place called x0, where the instantaneous rate of change, the derivative with x0 plugged in, is equal to the average rate of change, which we know is f of b minus f of a over b minus a. To draw you a picture of this, this would be if the, say, we had a function that was differentiable from here to there. We know that means it's continuous from here to there, and it's smooth, no sharp corners, no vertical tangents. So what we're going to say is, I don't know, maybe it looks a little something like that. Then the slope of the tangent line is going to be needing to equal the slope of the secant line. Now I'm going to just kind of in blue illustrate the slope of the secant line. And so that's going to be, I should probably get a straight edge for this. Again. Right there. Okay, so that's the slope of the secant line. That's f of b minus f of a divided by b minus a. There's got to be some place where the instantaneous rate of change, which is the slope of the tangent line, happens. Okay, so it would be right there. Okay, graphically speaking, this is what we're doing. We're determining, where this happened. Okay. Algebraically speaking, we're going to, take the derivative and solve where it's equal to this number if we're tasked with doing that. Okay, but I've got lots of that, in the notes book, in the lesson, in the homework, and all the experience you've had leading up to here. So I'm not going to do any more examples right here. Okay, in the second lesson, 3.2, we talked about all the things that we could conclude about a function by looking at its second derivative. And so we kind of started off with the idea like, hey, what if the second derivative is positive? What does that tell us? Well, if the second derivative is positive, that means the first derivative is increasing, and the first derivative represents the slope of the function. So maybe, the function was already having a positive slope, but that slope needed to increase. This would be a picture of f double prime greater than 0. Okay? But it doesn't have to be an increasing function, right? We learned that actually the second derivative being positive tells you nothing about whether the whether the original function is increasing or decreasing, whether the first derivative is positive or negative. So we could have a situation where we had a negative slope, but the slope was getting less negative, right? It was getting closer to 0, and that would be an increasing slope as well. Okay, we said that f is concave down. Concave up, right? It's going up. It's smiling. It has a positive attitude. Is concave up. And so that's where we said. Also, we could see, especially if we're looking at a picture of f prime, which we frequently are in situations in this class, that would be where f prime is increasing. And then we kind of had the same idea for concave down, and I don't think I need to talk you all the way through that. I'll just copy that in. Okay, so, and when that happened, maybe we were increasing, and we had a positive slope. But our slope is decreasing. It's getting closer to 0. That would be where it started to kind of curl down. Or maybe we had a negative slope here, and it was decreasing, so it was getting even more negative, and it's kind of getting close to vertical, so it's going to be hard for me to keep drawing that way, but I could draw over here getting less steep so that it was getting more steep as I went left to right. And these are both like, kind of frowning, that's what we said, but really the big issue is that the slope is decreasing where the second derivative is negative, and we call that concave down. And then we talked about places where the concavity changes. Now, a change in concavity, you already know, that's called a point of inflection on the graph of f. And I'm just going to definition real quick. You've heard me telling you about the definition of point of inflection, hopefully. I was yelling at you about it in class, I'm sure. I always do. And that's that it's a change in concavity which occurs at a sign change of f double prime. Okay, I cannot stress that enough, right? I'm not going to just yell at you through the video right now, but notice I have said nothing about f double prime equaling 0, except for that's not the definition of a critical point, okay? It's a sign change in f double prime, okay? Now, oftentimes, a thing is going to change signs at a place where it's equal to 0. But if we're talking about, just like the graph of f double prime, right? Graph of f double prime, and we're equaling 0 here, and then, maybe we're equaling 0 elsewhere, and then, I don't know, maybe we have a little jump discontinuity across the x-axis. That was causing some questions in class this unit. there's going to be 2 points of inflection, but not 3, okay? So this is not a point of inflection, although the second derivative is equaling 0, because before this point, f double prime is positive. F is concave up. Okay? After f double prime is still positive, f is still concave up. Okay? Right here, that is a sign change in f double prime. F double prime went from positive to negative. Right here, this is going to be another sign change on the graph of f double prime. F double prime was negative, now it's positive. These are points of inflection, and this is not. So you see that f double prime can equal 0 and not be at a point of inflection, and f double prime cannot be 0, f double prime being non-existent here. I was just marking, this is not like a point on the graph, this is just, I was emphasizing that point. F double prime cannot be 0 and still be at a point of inflection. So f double prime equals 0 just not any sort of suitable condition to give you evidence that you're sitting at a point of inflection. So when it says justify your answer for, you know, some sort of point of inflection question on the free response section of an upcoming test, you're going to say h of x took a point of inflection at these x values because h double prime changed signs. Just say that. Don't tell me that h prime went from increasing to decreasing. That works. That's not bad. But you know, the more that we get away from it's a sign change in the second derivative, the more we're getting closer to those responses that aren't earning the justification point. Okay, so I think that's all I've got to say about point of inflection. Now, the other thing we talked about in 3.2 was, I was going to just get a different color. I've been kind of sitting on red and blue for a while. Was the second derivative test. Okay, and so I'm just going to kind of copy in the rules here. This is where we're using the sign of the second derivative along with the fact that we're already sitting at a critical point to help us determine if we're sitting at a maximum or a minimum. Now, this technique is not going to work at the type of critical point where the first derivative fails to exist, because if the first derivative doesn't exist of a function, the second derivative is not going to exist either. Okay? But if we already know that we're sitting at a place of horizontal tangency, and we have a flat tangent while being concave up, so flat while concave up, right? The derivative is increasing. Then, okay, so this would be the graph of f. We know f has a local minimum. But also, we could say that, okay, if f prime is equal to 0 and f double prime is positive, that means that f prime is necessarily going from negative to positive, which is the first derivative test, knowing that we're sitting at a local minimum. Okay. Now, on the other hand, if f prime is 0 and f double prime is negative, and that means we're flat, horizontal tangent, while concave down. So I'll draw you a picture of f. That's the tangent to f. This is f, maybe extremely locally, but you know, looking at it, it's concave down while flat. That's going to be f having a local maximum. Okay. And local maximum, relative maximum, exact same thing, right? Just not absolute maximum. And I'm going to talk about that here in a second. Okay, I felt like there was something else. Oh, yeah. If f prime is 0 and the second derivative is negative, that means f prime is 0 while f prime is decreasing. So that means that f prime goes from positive to negative, which we know is the first derivative test is giving us evidence that we're sitting at a local maximum. Okay. Oh, and the other thing, just some advice I was going to give you about the second derivative test is that, we will use this kind of extensively in this class, but later in the class. So if you're getting ready for a Unit 3 test, I would say, first derivative test needs to be more prominent on your mind, because think about, we're always getting given a picture of the graph of the first derivative. We're getting an equation for the first derivative, or we're going to take the first derivative by hand and then, do a sign chart or sketch a graph on it. All of those situations, we have the full, complete picture of the derivative. In the future, we might not have the full, complete picture of the derivative. We might just have information at one point or something, or it might depend on y as well. And that will be when we're forced to use the second derivative test. You should not be forced to use the second derivative test at this point in the course just because you don't have enough tools under our belt. Okay, so I think that's all I've got to say about the second derivative test. Okay, I'm seeing that in 3.2 we also talked about using the calculator to find derivatives, but I'm going to say that if you need more support with that, you need to go watch a different video of mine or just come see me individually really for help. I don't think that doing a bunch of calculator stuff is going to be the best use of our time together here. So let's, before we move on to absolute extrema, let's fill out our grid. I think that's going to be the thing to do. Now, I know we already did this once in class, but I think it would be, it's never a bad time to fill this grid out. And, there will come a time later on in the year where just, I don't know, as a warm-up or something, I'll just order a bunch of copies of this and pass them out and have you fill it out again, because this type of stuff, it never really goes away. Okay, so a function f of x is increasing where as we move left to right, y is going up. Okay, so it looks like that. Okay, decreasing is where as we move left to down. Right? It could be a curve, it could be a straight line, it could be whatever. Okay, but we know our definition for increasing is where f prime is a positive number. Okay, and for decreasing, our definition is where f prime is a negative number. Okay, now I don't really have much to say. We know that f double prime doesn't really impact the increasing decreasing nature of the function, so I'm just going to say these are not impacting. Okay, I'm just going to kind of scratch through those. Okay, concave up. If we're looking at the original function and we're saying its derivative is increasing, well, it's going to be smiling, and so suppose we put little eyes on it to indicate that it's happy, it's concave up. Or it could be decreasing, but still, getting less negative and going towards a positive slope. Still, your slope is increasing. Okay, still happy, right, if we're putting our eyes on top. And then, as far as the first derivative, concave up is where the first derivative is increasing, right? So I'm going to say increasing. And then over here, that would be where f double prime is a positive number. Okay. Now you could say increasing. You could say it's where it's got a positive slope. If you're looking at a picture of f prime, which we frequently are, so you can draw it like that. Okay, concave down. Go a little faster here. That's where the derivative is decreasing, so the function looks like it's kind of angry. Maybe it had a positive slope, but it's getting closer to a zero slope. That would be a decreasing slope. And we put some angry eyes on there. Okay, we say that that's where the first derivative is decreasing. Okay, so down like that. And this is where the second derivative is negative. Okay. A point of inflection is a sign change in the second derivative, right? It's a change in concavity. So I'm just going to right now put that in there. Okay. And then a point of inflection would, on the graph of the original, it's where it's got an attitude change. It was frowning and now it was smiling and now it's frowning, right? Or maybe it was frowning and then it becomes smiling. I mean, there's a number of ways it can look. I mean, it could even come at a sharp corner, right? It was happy and now it's sad. It was supposed to be a little sadder, but not too sad to where it became not a function anymore. Okay, there's a lot of different ways that it can look on the graph of the original, but I'm not really familiar with any AP calculus questions where they're having you look at a graph of f of x and determine where the point of inflection is. That's not one I've seen before, is what I'll say. Okay, and then if we've got a sign change in the second derivative, okay, that means that f prime is going to change from, well, concave up is where, f prime is increasing and concave down is where it's decreasing. So it's going to be where it changes its increasing, decreasing behavior, which is what we would call a relative extremum. So if we're looking at a picture of f prime, which we frequently are, and we're trying to find the locations of the points of inflection, that's going to be where we're turning around. But we would like to call those relative extrema, or even better, sign changes of the second derivative. So, that could look like that. It could be at a minimum. It could be at a maximum. It could be smooth. It could be sharp, like, there's no telling. But either way, there's going to be a sign change in the second derivative if this is the graph of the first derivative. Okay, because the slope, or it's changing from increasing to decreasing. That's also a good reason. Okay, a relative maximum on the graph of f could come at a place where the derivative exists, or it could come at a place where the derivative fails to exist, right, at a sharp corner. So I'll just draw you a picture like that. I don't really know what else to say. That's where, in terms of the first derivative, the slope was positive, and then now it's negative. Okay, you might draw a picture of that happening. Okay, but that would, if you drew the picture and you only had that picture, you might forget about, the jump discontinuity possibility. And, like this one over here, it had a positive slope, and, maybe it was like that. And then all of a sudden it had a negative slope. Okay, so it could look like that as well. I really just focus on the positive to negative thing. And, if you're looking at a picture of the graph and you're like, oh, it was positive and now it's negative, that would lead you to believe that you were sitting at a local maximum, which is exactly what you would be. Okay, so yeah, and then, yeah, I guess I'll say for a relative maximum, if we're going to use the second derivative, that's the second derivative test, we would need f prime equal to 0, and we need both of these things, f double prime negative. Okay, because if f double prime is negative, that does not necessarily mean that you're sitting at a local maximum, right? We're not ever sitting at a local maximum on this, and this is very concave down. Okay, so that would be, yeah, I think that's a good explanation there. So for a relative minimum, it's going to be similar. It could happen at a sharp corner. It could happen at a point where the slope is 0. It's going to be where the derivative goes from negative to positive. And I'm just going to leave it at that because I know that that's going to be the best description of it. And if we were going to use the second derivative test, this would be where f prime was equal to 0 and, big and, f double prime was positive. Okay. And I just give a little more emphasis here. That these things right here that we're talking about, this is the first derivative test, and this over here, this is what we're talking about when we say the second derivative test. Now, this grid is pretty comprehensive, but there's one thing that it doesn't have on it that I always like to include every year, and that's a reminder of the definition of a critical point. And I said at the very beginning of this video, but we're kind of getting closer to the end, so I should probably remind you that a critical point is a place where the first derivative is either 0 or undefined, and those, nothing for us to say about f double prime there, but these are potential extrema. So that's what I'm going to say. But not guaranteed extrema, right? Because we could be, like I described earlier. Okay, so I would just say, okay, and you could do that, and it's still nothing to say over here for f double prime. You could remind yourself that it doesn't have anything to do with the second derivative. The critical point is where the derivative is 0 or non-existent. Okay, let's move on. Let's talk about absolute extrema. All right, so when we talked about absolute extrema, really the big topic of conversation was the extreme value theorem. So let me copy that in real quick. Right, and that was that a continuous function on a closed interval must take a maximum and a minimum on that interval. And so this would be a closed interval because it includes its endpoints. This is the same as like a to b this way, just to remind you. So when you hear them ask for the maximum and it comes with a closed interval, you know you're going to need to use the closed interval test, which we frequently call the candidates test. And I'm just going to copy those steps in real quick. You've already got them in your notebook. You've done this a few times. Okay, so what that looks like is we're going to be finding the maximum or the minimum value of a function over a closed interval that they're going to give us. Okay, we're going to evaluate f at the endpoint. So it's going to be like, okay, f of a equals some number. Okay, find that out, depending on the function. F of b is some other number. Okay, we got to check those endpoints because sometimes that's where the maximum and minimum will occur, and that's always where the justification point is coming from, partially. I mean, you're not getting the justification point if you're not checking the endpoints, is what I'm saying. Okay, so that's me checking f at the endpoints. Evaluating f at the critical points, that's going to be, you're going to need to start with f prime of x equals 0, and then you're going to get some x values, so, say you get 2 of them that are in between a and b. That's the worst case scenario. Really, the worst case scenario is you get a bunch of critical points on the interior of the interval you're interested in. Okay, if you get 2 of them, then we're going to go back and we're going to evaluate f at x0, and we're going to get another value, and then, f at x1, and we'll get another one after that. Okay, if you want to see examples of this, just go watch me do the 3.3 homework, and there's plenty of candidates test problems there. Okay, then we're going to find the desired max-min value. Okay, so that's just going to be from these. If we're looking for the actual maximum value of f or the minimum value of f, it's going to be one of these numbers right here that we found by computing f of a, f of b, f at a critical point, f at a different critical point, right? And I never recommend excluding critical points because they're not the right type of extremum. And I talked about this in class. I'll talk about it more with you if you're interested, but as far as getting the points on free response, you're going to want to just put all of the critical points that are between A and B in your table or just in your list of things you've tried, okay? And then the desired values thing, I'm going to give you advice to be careful and really read for what they're asking. Sometimes they ask for the value of f. Sometimes they ask for the x value or the time value or the input value where the maximum or minimum is occurring. So, careful there, looking around for what your actual answer is going to be. Is it going to be an x value or is it going to be an f of x value? Okay. I think that's all I've got to say about the candidates test for now. It's not going to be as big of a deal in this unit as it is as we move forward through the course. Let's talk about motion. So in this unit, we studied rectilinear motion. And in calculus AB, that's all of the motion that we do, right? In BC, we will let the object break off of just the straight line that it's traveling on, and that's what it means, rectilinear motion. Object is traveling on a straight line. Frequently the x-axis or the y-axis. Okay, pretty much always the x-axis or the y-axis, especially at the beginning. Maybe as we move forward and get some more tools, we'll talk about a train on a track or Kathleen skating on a straight track. I remember that free response problem. We've got some situations that we can look at. But for now, I think we can settle with just an object moving along the x or the y-axis because we're just getting started. So oftentimes they'll give us a position function. So that's the actual coordinate of the object on the x-axis or the y-axis. Okay, that's usually going to be, let's just say x of t. Let's assume it's moving along the x-axis. Okay, what I need you to know about velocity and acceleration is that velocity is, we usually write v of t, and that's the derivative of position. Okay, and that acceleration, we usually write a of t, that's the derivative of velocity, which is going to happen to be the second derivative of position. And those are like the most basic, most important facts that we need to know about position, velocity, acceleration, is the derivative relationship there. Okay, and then I've got a few things that we need to be aware of, like at rest is going to mean velocity 0. Things not moving, its rate of change of position is going to be 0. That's why velocity would be 0 at rest. Okay. And we need a definition of speed. We need a few things. Okay. Yeah, but I'll talk about speed kind of separately because it is so separate from position, velocity, acceleration. Okay, so I said at rest, that's going to be where velocity is equal to 0. Okay, moving left, if we're on what am I saying? If we're on an x-axis, moving left is going to be where velocity is negative because the position is decreasing. The actual, the x-coordinate is getting less and less. Okay? So the value of x is decreasing, and so we would say x prime is negative. X prime, that's velocity. Okay, moving right, that's going to be the opposite. V of t is greater than 0. Changes direction, that's going to be a sign change in velocity. I'll put that in there. For moving on a straight line. Right? So it's going to be a sign change in V of t. Let me look through the booklet and make sure there's not any other kind of word clues that I'm forgetting. Nope, those were the 4 that I copied in the notes book, so I think that's probably the 4 that we need. Okay, now I think we should probably talk about speed here, and I'm going to do that completely after covering all this up, right? It's a completely different topic. Okay, so for speed, I'm thinking, let's define it. Speed is equal to the absolute value of velocity. And we're going to talk more about this as we move forward in the course. This is not going to be our only treatment of particle motion. We're going to come back and do actually a whole lot more with this once we learn how to anti-differentiate and what that would even mean. But basically that's just going to be recovering a position function given a velocity function. That's where we're headed. So speed is going to be the absolute value of v of t. And so speed increasing versus speed decreasing. And it's kind of a shame that we don't get to talk more about the absolute value of functions or, just kind of the nature of what this does to derivatives and things, because it would be really interesting. There's just so much that we have to tell you about in AP Calculus that we can't really get into this. And I would love to talk about, when is the absolute value of f of x increasing versus not and derivatives. But there's just no time. So we do talk about it with speed, though, and speed is an absolute value function at its core. So speed is increasing. That's going to be when the absolute value of v is increasing, right? So speed could be positive and getting bigger or negative and getting more negative. Okay, so the test I like to use in my class is going to be take velocity at a particular time, speed increasing at t equals, some special time. That's going to be where if velocity and acceleration have the same sign, right? But the test I like to use is the product of velocity and acceleration. That's going to be a positive number. Because again, if velocity is positive and increasing, then velocity and acceleration would both be positive. And its absolute value would be getting bigger. If you think about it on a graph, it's getting farther away from the x-axis. Okay? But if the velocity was negative and getting more negative, it would be going farther from zero. The absolute value of v would still be increasing, and negative times negative is still positive. In the next calculus class, you could use a similar test if v and a were both vectors, and it would be the dot product of v and a, but coming back positive would indicate that the speed was increasing. And so that's why I like to use that in this class, because I know a lot of people in my class end up undertaking multivariable calculus. And it would be nice if it was kind of the same test, just a different meaning of times, as opposed to, in single variable, it's same sign, different sign. I think that's too much to worry about. So speed decreasing that's going to be, again, at some special time. That would be where speed is getting closer to zero, right? And so velocity is getting closer to zero from the positive or negative side. And the test for that is going to be that velocity multiplied by acceleration is negative. Okay, I'm thinking that that's all I'm going to say about speeding up and slowing down. Now, all of a sudden, I'm remembering another problem type that I need to show you about. I don't know if it's going to be on the test this year, but who knows? I'm going to use this video in future years, so maybe you're watching this in a future year, and I'm going to use this next problem I'm talking about on the test. But I think this is all I've got to say about speed increasing versus decreasing. All I've got to say, hold on. Speed increasing, that's what we would call speeding up. I think I've just kind of been using this interchangeably, but I know that for people that for whom English is not their first language, this is kind of an issue sometimes, especially if you're not super confident with speeding up and slowing down, exactly what that means. You haven't been speaking English your whole life and talking about it in a car, then that could be confusing. So I just want to be real clear that speed decreasing is the same as slowing down. Okay, and yeah, but if you're asked about speeding up and slowing down and you just say, the acceleration's negative, it's slowing down, don't do that. You're not going to get any credit. That's completely misunderstanding the nature of the question. And it happens every year, but I'm hoping that this year is the year where I have way fewer to maybe no people doing that. All right, so, there was one more thing I wanted to say about rectilinear motion. So, go over here, bring that page back, put it up top, and talk about moving toward the origin or away from the origin. I think this is the type of thing that probably showed up in a homework problem this year, but because since I already had recorded the homework solution videos last year, I haven't worked the problems this year, and so I haven't seen it. Okay, toward or away from the origin. Okay, really fit that in. Okay, so if, again, I'm going to assume, working on the x-axis. Okay, that's going to be the origin. That's going to be x equals 0. Okay, let's just think about let's draw a picture of what it would mean to go toward. Okay, I could be over here, and okay, I could be over here where x is positive and going back towards the origin, and that would be, well, okay, x of t is positive, but velocity is negative because I'm moving to the left. Okay. But it could also be the other situation, right? I could be over here, I could have a negative position and a positive velocity. Okay, so okay, I don't think I've left myself enough room there, so I'm going to just give myself more. Or I could have x of t is negative and velocity is positive. Okay, you could say opposite signs, but this doesn't come up all that often in Cal AB on the free response. It's pretty infrequent, but not never. It's not like it's never come up. And my advice to you is that speeding up and slowing down is pretty common. It's worth memorizing the test. Multiply V and A, check the sign. This, I don't think, is worth memorizing the rule. So if you are, confronted with a problem like this, I would recommend you just draw a diagram, just keeping in mind, I need to think about the position and the velocity. That's what's going to tell me what direction I'm headed, right? Where I am and where I'm going. Okay, so away from the origin is just going to be the opposite. So I'll just go a little bit faster here. That's going to be my origin. I could be having a positive x value and a positive velocity. I could also be having a negative x value and a negative velocity. So this would be x of t is greater than 0 and v of t is greater than 0. Or it could be x of t is negative and, x of t is decreasing, which would be where its velocity was negative. Okay, I think that that's going to be all the particle motion situations that I need to tell you about for this year. Let me just look through one more thing. Oh, yeah, and so it's something not really for this test, but something that I want you just to make you aware of as we move forward in the course, is that occasionally they'll ask questions about, the behavior of objects as t approaches infinity, and that's not going to happen on your upcoming test, right? But it might happen somewhere along the way in this class, and if you're just reviewing Unit 3 and, beginning particle motion, might as well start mentioning it now. If they ever talk about t approaching infinity, that's got to be a limit, right? An infinity-involved limit. And so, probably won't be helpful to you in the next couple of days, but might be something coming up over time. Okay, that's all for particle motion, and that's all I've got to say about Cal BC Unit 3. This one was pretty long, but this is really, a heavily represented topic on the AP exam, so I think it was good that we talked a little more in depth about our definitions. Thanks for watching. Hope this helped.